Welcome to our discussion on differentials. So this is the second part of this topic, no, that we got last in the last video. Okay, so we're now going to focus on the application of differentials. But before we go to that, let us have review of what we had done last time. So I think last time we missed to answer, no, the question like are these approximations overestimates or underestimates. So what we're going to do, class, just compare your answer. No? You can use your calculator, your gadget to calculate the values for this one. Okay, and then just compare it with the results of our calculations. And it's up to you to answer this question. Are these approximations overestimates or underestimates? Okay, so now let's proceed to differentials. So if a function f is defined by the equation y equal to f of x, the differential of y, denoted by dy, is given by this. So dy equal to f prime of x multiplied by dx. So actually that one, class, is just taken from the uh, basic derivation, that if you have y equal to uh, function of x, now if you are going to differentiate both sides, so differentiating both sides with respect to x, so we have dy uh, divided by dx, or dy over dx, equal to, so our right side becomes f prime, no? We have f prime of x, then just multiplying both sides by dx, or you just cross multiply dx to the right, so we have dy equal to f prime of x times dx. Okay, so that is where that equation is coming from. Okay, so this one here is just derived, no, from this basic differentiation. All right, now where dx, so the dx here, this dx is called the differential of x. This is called differential of x, and is equal to delta x. So our dx is equal to delta x. When dx equal to delta x is small, the value of dy is a good approximation of the value of delta y, which is equivalent to f of x plus delta x minus f of delta x. Okay, so where this equation coming from? So this is just, if you look at the video class on our derivation of the slope, no? Slope of the line, something like this. So we have here the x-axis, and we have here the y-axis. And if you have this, see this graph of the function. Okay, so this is our y equal to f of x. I hope you still remember this one, class. Huh? So we have here, say, point P with coordinates. Say, for example, if the distance from this point P from the y-axis is equal to x, all right? So it means that these are x here. Okay, so the height of the function, height of this point, from the x-axis. So this is what we call f of x. Now, if we are going to move the point P along this curve, say for example at this point here, so say this is our point Q. So if we move the point P towards that point, so there is a corresponding horizontal distance, and we normally call this as our delta x. This is the displacement, no? As the point P moves from P to Q. So we have here the horizontal distance, we call it delta x. And the total distance from the y-axis towards that point Q. So this is now the sum, no? The sum of x. So this is x plus delta x. So that's why the coordinates of point Q. So the coordinates of point Q is x plus delta x, right? And f of x plus delta x. So it means we have here the height of the function f of, so this is x plus delta x. So what is this f plus x, or f of x plus, so this is plus here, f of x plus delta x. So this is actually the height, the height of this function, height of this the value of the function at this point. So this is our f of x plus delta x. All right, and we know that this one, the height of this is f of x. So here the height of this is f of x. So therefore, this part here, I'll change the color here. So this is actually our delta y. So delta y here is the difference. This is the difference between this height. So this height, which is f of x plus delta x, minus f of x. Alright, so delta y here is f of x plus delta x minus f of x. So that is taken from this. This was derived in our discussion on the slope. Okay, so the value of dy is a good approximation to the value of delta y, which is equivalent to the f of x plus delta x minus f of x. So I just give you the simple recall of what or where this equation coming from. Okay, so the differential of y is given by dy, which is approximately equal to delta y, and this is equal to f prime of x dx. Now take note that dy, from our derivation a while ago. So the dy is just equivalent to f prime of x dx. Sorry. And this is equivalent to f of x plus delta x minus f of delta x. Alright, so our dy therefore is approximately equal to this one. Right? Okay, so to solve for, if you are going to solve for f of x plus delta x, so this one, so we just need to transpose, you just transpose this part here to other side and then change the sign. Okay, and then what remains on the right side is this one, and we just interchange side. So this one, when you transpose this, so this becomes positive. So that's why we have here positive f of x added to f prime of x dx. So this one here. Okay, so for example, if we are given here a problem, the radius of a sphere was measured and found to be 21 centimeter with a possible error in measurement of at, at most 0.05 centimeter. What is the maximum error in using this value of the radius to compute the volume of the sphere? Okay, so here in this problem, so we're given, so it's better class to write down the given, no? This will help us analyze on and also help us figure out how to solve this problem. Okay, so we're given here the radius. How much is the radius? Okay, so the radius is equal to 21 centimeter. Okay, with a possible error in measurement. So what does it mean, class? Assuming here the problem mentioned about sphere. So sphere. So paano itsura ng sphere, class? Alright, so it's just like a circle. Sorry, it's not perfect circle. Alright, so it's something like this. It's circular. So since that is sphere, so assuming this is the center. Okay, so we have here the radius. So this is a sphere, so more or less it will look like this, right? Or something like this. So this is the radius r. Now we have here possible error in measurement. So it means that if this is our r, it can be that r is more than this, no? Maybe lumagpas siya. Okay, so there's a discrepancy of, okay, so perhaps the original r is from here to there, or perhaps the measure is up to here only. So there's a short, more or less there is a plus or minus, no, from the exact value of r. So this part here, class, this is what we call the dr. This is the error. No? The error is expressed in terms of the differential of this r. Okay, so we're given dr, so which is equivalent to 0.05. So it's not mentioned if it's more than r or it can be less than r. So generally we can have the plus or minus, no? Plus or minus 0.05. It's 0.05. Okay, so our dr is equal to 0.05. Okay, and then we are required to, so what is the requirement in this problem? So what is the maximum error in using this value of the radius to compute the volume of the sphere? So again, we are asked to find the or calculate the maximum error. Okay, so we are required to. So what do you think is required in this problem, class? So what does it mean, maximum error? And it mentioned about the volume. So if that is the volume, so we have volume, and then like in r, so we have r, exact value of r, and there's an error. So this is our dr. So we speak of volume, and then we talk of maximum error in using this value to compute the volume of the sphere. So it means the error of the volume, or the dv. Okay, so this is what is being required or asked in the problem. Okay, so the solution is, first we need to know, no, what is the volume of the sphere. So in our previous mathematics, so in our solid mensuration, so we have here the volume of the sphere is equal to 4 over 3, 4 over 3, then pi r cubed. So can you still remember this? Still familiar or remember this equation of volume gas? So that is the first thing that we need to know. Otherwise, we cannot solve this problem. Okay, so here's our answer. So we start with the volume of the sphere, which is given by this equation, V equal to 4 over 3 times pi times r cubed. So take note, 4 over 3 is a constant. Pi is also a constant that is equivalent to 3.1416 approximately. So therefore, we have here volume as a function of the radius. So we're asked to find the maximum. So when you speak of maximum class, it talks about uh, in the topic maxima minima. So this gives us hint, no, what to do. So maximum, so we have to differentiate this. Now when you differentiate, all right, so I'll write it in the other screen. So we have volume equal to 4. So volume is equal to 4 over 3 times pi times r cubed. Okay, so differentiating both sides with respect to the radius, so we have here the derivative of the volume with respect to r, okay, equal to, so this is constant, no? 4 over 3 times pi is a constant. So we'll use the formula for differentiation rule, no? Derivative of a constant times u with respect to x. This is a constant multiple role class. So we have constant times the derivative of u with respect to x. Okay, so we'll apply that formula or that rule. So we have constant. Our constant is 4 over 3. Okay, 4 over 3 multiplied by pi. And then applying the power rule, because our u here is in terms of, so we have to use derivative of u to the n, right? U to the n with respect to x. So equal to n times u to the n minus 1. N minus 1. Sorry, n minus 1 times the derivative of u. If we use the general power rule, derivative of u with respect to x. Okay, so we'll use that formula. So therefore, this is a power rule, or you can use general power rule. So the power or the exponent will go down, okay, and then multiplied by the constant, then multiplied by, we have u, our u here is r, then raised up power n minus 1. Rn is 3, 3 minus 1, so that becomes 2. Okay, so raised to a power 2. Okay, and then derivative of u with respect to x, our u is r, so derivative of r with respect to r, so that is equal to 1, so no need to, so because times 1, this is just times 1, because derivative of r with respect to r is equal to 1. Okay, now solving for dv, we just cross multiply dr or multiply both sides by dr, so therefore we have dv is equal to 4, we have 3 at the numerator, and we have 3 at the denominator, so 3 divided by 3 is equal to 1, so what is left is 4 pi times r squared. All right, and then you cross multiply dr, or when you multiply both sides by dr, so we have now dr on the right side. Okay, so now solving for the maximum error of the volume, or we have the dv, so just substitute the given. Right, so we have 4 pi multiplied by r. Our r is given as 21 centimeter squared. Okay, so 21 cm squared, so you square this one, and our dr is equal to 0.05 cm. Okay, so multiplying, so we have dv equal to, what is our dv? So dv is approximately equal to, I think that is 277. Try to check less. And then the unit here is in terms of centimeter cube. Centimeter cube. Because you square cm, so cm squared times cm, so that would be cm cube. So this is approximately, no? Approximately equal to. Okay, so that's what is shown here. So that is approximately equal to 277 centimeter cube. All right, so that's one of the applications of this topic, differential. Solving the to solve the error approximate values. Okay, so another application is finding the approximate value of the given radicals. All right, so we're given here three items. So I will solve this quickly. Then perhaps I'll give you this for your practice. Okay, so find the approximate value of the following radicals using differentials. And I think class, to make shorter, no, the video, because it's very hard to watch longer video, so I will make another video for this part. Okay, so I will stop up to this part here and just see you in our next video for the solution of this first item. Thank you very much. See you in our next video. Bye.